Warm welcome to Yokogawa Test and Measurement. My name is Markus Ottomeyer. I'm responsible for marketing communication at Yokogawa Test and Measurement for the German market. And in this role, it's my honor to welcome you to today's webinar with our optical measurement specialist, Sebastian Grischka.
Hello.
And now I'll step out of the picture and give you the full view of the measurement setup for today's key question: how to measure pulsed laser sources effectively. Sebastian, what have you prepared for us?
Thank you, Markus.
Welcome.
Hello and welcome to today's webinar. And today I will talk about measurement of pulsed light sources with our Yokogawa spectrum analyzers. So now I will come to the topics. First, I will talk a little bit about the general challenges that we are facing when we want to measure pulsed light sources with our grating-based scanning spectrum analyzers. Then I will talk about how Yokogawa is facing these challenges and what kind of solutions we are preparing. And then I will step through different pulse condition and repetition rates and see what the adequate measurement techniques for these kind of signals will be. So we will have a look at the time average spectrum mode for different frequencies. We will have a look at the max hold function, and we will have also a look at the dedicated settings for pulse light measurement that our OSAS has integrated. And at the end, I will give a short outlook about the feature and benefits of our new instruments that even improve the capabilities for pulse light measurements. Pulsed laser sources are used in very many many applications and in many different operation states, from high to low repetition rates and with longer and shorter pulse width. These lasers are used, for example, in material processing, telecommunication and optical communication, in biomedical imaging and treatments, in spectroscopy and metrology. When you want to measure these different kinds of pulse sources with a spectrum analyzer, you have to be careful and pay attention to the right measurement techniques and the characteristics of our devices that you can perform appropriate measurements of your source. So you have to take the pulse conditions in consideration as repetition frequency of duty cycle and the characteristics of our grating-based OSA, which is a scanning system. And to achieve an accurate spectral analysis of your laser source, it is important to understand both your laser and the operating conditions and the capabilities of our spectrum analyzer. An OSA measures the total power of a specific wavelength segment while sweeping the optical wavelengths and displays it as an optical spectrum. So the energy is sweeping by the sensor. And in standard operation, we are assuming that there is a constant input signal during the sweep, like a continuous waveform. Pulsed light, which rapidly turns the signal on and off, is not expected in the normal OSA operating conditions. When you have pulsed light, it may lead to a segmented spectrum, or it may lead to measurement errors due to interferences with the amplification circuit of the spectrum analyzer. And when you do not take appropriate measurement techniques, the measured spectrum may appear segmented or chopped due to the temporal variation of the signal during the wavelength sweep. To face these challenges, Yokogawa offers different types of measurement methods. First, we have the time average spectrum, which is somehow the normal measurement mode which the spectrum analyzer is working in. Then we have one simple possibility to capture even transient signals, which is the trace hold, the trace max hold, which captures the maximum value over several sweeps. And we also have different pulse light measurement settings implemented in our devices that we can also get along with different operating conditions and requirements to the measurement. Before we come to the different settings, I will give a short introduction about the capabilities of our OSAs and what needs to be taken in consideration. Our spectrum analyzers come with different sensitivity settings. Each sensitivity setting has its own dedicated amplification circuit. And the sensitivity setting you are selecting determines which amplification circuit is selected. For each different amplification circuit, the gain and the response speed of the sensor and amplification circuit are inversely related, which means when you want to have a higher gain to get even weak signals measured, this leads to a slow response speed of the spectrum analyzers and may also lead to a slower wavelengths sweep, and the measurement takes more time. If you want to make faster measurements, you need to select an amplification circuit with a lower gain, which then enables faster measurement speeds. But the sensitivity settings do not only affect the measurement speed of your sweep, but also the power detection method. As I said before, the amplification circuit and the amplification and the response speed are inversely related. And this can lead to not measuring the full power if you have short pulses and having a high sensitivity setting, because the short pulse may pass by faster than the whole amplification circuit has detected the complete signal. So if you want to detect the full power of the signal, a lower amplification is usable to get a faster response speed. And if you want to detect lower sensitivity levels with a high amplification, then you need to take more time for the measurements. The OSA settings not only affect the quality and the duration of the pulse measurement, but also the quality. In time average mode, the sensitivity settings limits measurable pulse repetition. And in the external trigger mode or in the peak hold mode, the minimum pulse width is limited by the reaction speed of the device. These are all related to the response speed of the OSA detection circuit. So let's have a look at the different thresholds where we need to take things in consideration. If we have high repetition frequencies from above 10 megahertz and more, then we can just use the time average mode, which is the normal operation mode of our instruments. Then no extra considerations need to be taken, because the pulse repetition frequency is much higher than the response speed of the device. And so if you have signals with high repetition frequencies above 10 megahertz, they are realized as a quasi-continuous waveform for the unit. If we then reduce the repetition frequencies and go below 10 megahertz, then we have to take in consideration the behavior of the unit, and we can cover all these different repetition frequencies in a given range with different sensitivity settings, which I will explain later. If we then come to lower repetition frequencies or to irregular repetition frequencies or frequencies below 500 Hertz, then in the normal measurement mode, a complete and high quality measurement is difficult, and therefore then the different settings for pulse light measurement should be used to achieve a proper spectrum. What also needs to be taken in consideration is the pulse width of your signal. If you have pulse width of less than 50 microseconds, then these are fast enough that you do not need to take any considerations, and they're captured well in with all sensitivity settings of the device. But it can only be measured a time average spectrum, and the peak power of pulses shorter than 50 seconds cannot be detected by the unit. If we have pulse width of 50 microseconds or larger, then we have different settings for peak detection that enables us to measure the full power of the pulses. First, we have a look about the measurements and capabilities of high frequency pulsed sources with a frequency of 10 megahertz and more. For this high repetition frequencies, the reaction speed of the detection circuit in the OSA is slow enough, even at the lowest sensitivity settings, so the OSA can measure it like a continuous wave, regardless of the device settings. Therefore, the sensitivity needs to be set according to the average power. The power that is then given by the instruments when you do your measurements is the time average power of these pulses, which is calculated with the peak power of the light pulse that was measured by the device and the duty ratio of the pulsed light. In this mode, you do not need any external trigger or any other devices or utilities to trigger the settings. But in this mode, irregular pulses cannot be handled because it's only the average power can be measured. And if there are fluctuations, they just cannot be detected. But one benefit of this standard measurement mode is that all additional capabilities and settings of our OSAs, like the chop mode, the SMSR mode, the double speed mode, or the averaging function, can be applied. And if you are also having high frequency repetition rates and low pulse width, you can even measure signals with a pulse peak power of more than 1 watt. But this needs to be done carefully that the instrument is not overpowered. Now, I change the slide. So let's have a look at the pulse width. If we are having a pulse width that are larger or longer than 1 microsecond, then the pulse peak power is determined by the maximum input power of the OSA. Here today we are making some demonstrations with an AQ6370E. And for this unit, the maximum input power is 25 dBm or 316 milliwatt. And if you have pulses longer than 1 microsecond, even the pulse peak power must not exceed this value. When we are coming to a pulse width of less than 1 microsecond, then the time average mode can even deal with higher pulse peak powers than 1 watt. And as you can see here in the table, can somebody see my mouse? Yes. Here we can see the relation between the pulse width, the pulse peak power, and the repetition cycle, and how much power can be applied. But we see, even if we have high repetition rates with a very low pulse width, the overall pulse peak power must not exceed 316 watt. So always be careful how much power you apply to the instruments, not to destroy or overpower the sensor. If we are then coming to repetition rates that are below 10 megahertz, it can be difficult for the instrument to capture the full spectrum or to achieve a good measurement and high power reading. And if we have lower repetition frequencies and fast measurement modes, there may be disturbances of the spectrum due to the impact of the frequency response of the amplifier circuit, or that not the full pulse can be captured. But for pulse width between 10 megahertz and down to 500 hertz, we can adjust the sensitivity settings of the OSA, that we can even measure low repetition rates down to 500 hertz. And if we are not able to capture the full signal with these settings, one simple technique to capture the full spectrum is the trace function max hold, where we then, with a repeated trace, can capture also the signal of different pulses, and they are just graphically combined on the screen, as you can see here, where we can see the spectrum of a Fabry-Perot laser, which was measured with a repeated sweep in the max hold mode, and we can see that the shape of the spectrum is improving, and with every repetition we get more information about the spectrum. And to show you how this is working, we will now make some demonstrations with our spectrum analyzer. Now I switched to the remote control monitor of our spectrum analyzer, and I will now use a regular DFB laser that is powered with one of our Yokogawa source measure units, and we will see how the analyzer is reacting to different operating conditions. So now I'm driving this laser with a little bit of tech current, and with a signal now with a pulse width of a repetition rate of 100 microseconds and a pulse width of 50 microseconds. As we have seen before, this is not the highest repetition rate that the instrument can use, so we have to take some considerations. And as we see, a repetition rate of 100 kilohertz is 100 microseconds is the same as 10 kilohertz, which is much below the 10 megahertz that we were given for the frequency, that we do not need to take any extra considerations. And if we now make a normal measurement in this with the lowest sensitivity, then we see a disturbed spectrum, because the sweeping speed is too high that for each measurement point the full spectrum is detected, and the distortions due to the switching of the laser can be seen. If we then increase the measurement sensitivity, we get a much improved spectrum, but there are still some disturbances due to the repetition frequency. If we then go even to a little bit higher sensitivity, we see we can capture the full spectrum almost without any disturbances. Now I switched to sensitivity setting high 1. That can even detect slower repetition frequencies than we have applied at the moment. Now I am increasing I'm decreasing the repetition frequency, and now we have a period of 1 millisecond and a frequency of only 1 kilohertz. The spectrum still can be seen with the full shape, but the power reading has decreased because we still have the same pulse width, but the repetition period has strongly increased. If we now increase the pulse width a little bit, we see that also the power reading of the spectrum is increasing because the duty cycle is getting shorter, and therefore the time average power that is detected by the unit is increasing. If we then go to even higher repetition periods, now we have a repetition period of 5 microseconds, and we can see that the spectrum again got disturbed. If we now go even to a higher sensitivity settings, we can see that even this signal still can be captured. But this is a little bit slow, so let's now I've set a repetition frequency of 1 kilohertz. So we can measure it with a little bit higher sensitivity and achieve a higher measurement speed. And as we see in this operating condition, we have a peak power reading of about 2 dBm. If we now change a little bit the duty cycle, now I'm reducing the duty cycle a little bit, and due to the time average spectrum and time average power measurement, we see a decreasing power level. And if we then increase the pulse width, we see that also the power reading is increasing accordingly. So we see in the time average mode, we do not know the exact pulse power of our peak power of our pulses, but it's an adequate measurement mode to measure the spectrum of high repetition sources. If we then change the timing a little bit again, and reduce the measurement sensitivity, we again see a disturbed spectrum. And now I will just shortly show the benefits of the max hold function. And when I enable the max hold and doing measurements in a repeated sweep, then with every sweep, we can detect more of our signal, and the shape is really strongly increasing. But until all pulses are captured, it can take some time, and this is a quite time-consuming way to measure your spectrum. And we still have the constraints of the time average power reading. If we are then more interested in the absolute power reading of the pulses, then we can go to our integrated pulse light measurement modes. And now we first exactly. Now if we want to measure the peak power and not only the time average power, then we can use some of our dedicated pulse light measurement settings. Our devices come with 3 dedicated settings for pulse light measurement: the peak hold mode, the external trigger mode, and the gate mode. But there are some limitations coming with the pulse light measurement functions. The high dynamic range mode or the chop mode is not available. Also, the double speed mode and average functions are also not available. And special functions like the side mode suppression ratio can also not be used. And to detect the peak power of the pulses, we have some requirements regarding the minimum pulse width. First, we have a look at the peak hold mode. The peak hold mode captures the peak value within the repetition cycle of the optical pulse. Pulses with at least 100 microseconds are required to capture the full peak and the full peak power. In this measurement mode, we do not need any external triggering for controlling the instrument. And we can measure the real peak power of the input signal. The measurement sensitivity settings are determined by the minimum pulse width that we have with the signal. And we see at the lowest sensitivity setting, the norm hold, we can detect it in this, in this mode detect the full pulse power of peaks with a pulse width of at least 100 microseconds. If we then need to increase the sensitivity settings to deal with lower power levels, then we need longer pulse width that the full power can be detected. If we are measuring in high sensitivity modes with lower pulse width, then again, not the full peak power is detected. And for these settings, the power reading is also again some kind of time average power reading. In the peak hold mode, then we have additionally set the peak hold value, which is determined by the repetition frequency. The peak hold value can be set from 1 microsecond to 9,999 microseconds. And therefore, with this mode, even low repetition frequency of 0.1 Hertz can be measured. The hold time always needs to be set higher than the repetition rate or the inverse repetition frequency. Now we have a look at the peak hold mode. I switch back to the Now we are coming back to the instrument. And we go to the settings and enable the peak hold mode. Here we have our settings for pulse light measurement and other setup points. And here we select the peak hold function and now have set a peak hold value of 3 milliseconds. The laser now is operating with a repetition frequency of about 1 kilohertz, which means a period of 1 millisecond. So we are higher with our peak hold value. If we now make the measurement, we see that we are already detecting more power of the pulse than before in the time average mode. But as we now have a pulse width of 200 microseconds, in this measurement mode, we cannot detect the full power. So now I will reduce the pulse width to 100 microseconds, which is the shortest pulse width that can be measured in this mode. Now I'm also switching to the norm hold mode. And we see we can detect almost the full spectrum, but due to the sensitivity settings, we have a strongly increased noise floor and cannot evaluate the real noise of the laser. The only thing we can see is the noise of the instrument. But as we now have a pulse width corresponding with the sensitivity settings, we can now measure the full peak power of this pulse. Now I increase the sensitivity a little bit and go to longer pulse width. We see here that we can detect the pulse peak power. And even if we now change the duty cycle of the laser, before, when we were changing the duty cycle in the time average mode, also the power reading changed because of the different duty cycle and that the power was calculated from the average. If we now change the pulse width and therefore increase the duty cycle, we see a little shift in the spectrum due to the higher energy that is applied to the laser, but the peak power still is the same and is not changing with different duty cycles. So we see that with this mode, really the pulse power of the peak is detected. In this mode, the measurement, the minimum pulse width that can be completely measured is 100 microseconds. If we then go to the other settings for pulse light measurements, we can even detect pulses down to 50 microseconds. And for this, we will use the external trigger mode. The external trigger mode performs sampling in synchronization with an external trigger signal and so measures the pulse light. For this mode, as the name is already suggesting, we need an external trigger signal synchronized with the optical pulse. One benefit of this is that we can even handle irregular pulses. And the minimum pulse width that can be completely detected is decreased down to 50 microseconds. Since the peak power of the optical pulse is captured, the optical power measured is higher than the one in the time average mode, as we already have seen in the peak hold mode. Problems due to insufficient power of the source are unlikely to occur, and measurement can be done faster with a high dynamic range, and it can be even secured with low sensitivity settings. For using the external trigger mode, we have a trigger connector at the back of the instruments, but you cannot see. So we need to connect the trigger signal from the source and adjust the trigger settings if we are triggering to the falling or rising edge. And then with each trigger signal, one sampling point is measured. To capture the signal properly, we also have a setting for adjusting the delay that we can capture the full pulse and can so reduce the measurement speed. So now we will see how the external trigger measurement is working. I have now connected the signal from the trigger signal from the source to the spectrum analyzer, and now I change it to the external trigger mode. In the trigger settings, the trigger function is set to the falling edge, and we have set a trigger delay of 11 microseconds. And if we then start the sweep, we can see that with each trigger signal, one sampling point is measured. Oh, now I change to the instrument. To demonstrate the full capabilities, I now reduce the pulse width down to 50 microseconds and start a new measurement. We still can see that we are getting a little bit distorted spectrum. So we need to adjust the trigger settings. Oh, and I also again need to reduce now I've set the period for the signal to 100 microseconds and the pulse width to 50 microseconds. We have also selected a quite low sensitivity. And we can now see that there are still some disturbances. And it also looks like that we forced the laser to get in, due to the changing duty cycles, we obviously forced the laser to leave his single mode operation mode. And now we can even see that some multi-mode operation has occurred. This was not planned, and I'm not sure what happened to the laser. But we can see that with a triggered measurement, we can quickly capture the full signal. But we still have some multi-mode operation. This was not expected. But I can also show you one more benefit of the triggered measurement is that we can also deal with irregular pulses. So I now will apply a small program that I created that is now working with irregular pulses. And if we Now look at the instrument. I don't know if you can see that the percentage of progress of the sweep is not changing equally. So we have now pulses with different pulse width, different repetition frequencies, and also this can be handled in this mode easily. Also in this mode, normally you would see that always the peak power of the laser is detected. But as my laser now changed to multi-mode operation, the peak power got a little bit difficult to determine. So let's see if we get it back to a normal operation. No. What is the laser doing? But we can see also the irregular pulses now can be measured in this mode. Now we make a stop and stop the sweep. Now we are back in the normal pulsed operation mode. And we are again getting a better signal. Now we are coming to the last dedicated setting for the pulse light measurement, and that is the gate hold mode. The gate mode. In the gate sampling mode, the instrument only measures the data when the gate signal is active during sweeping. This application is very useful for periodic or transient signals, like they are also occurring with burst signals, or a common application for this in the telecommunication are measurements of recirculating loop tests. In this measurement mode, the instrument performs complete sweeps according to the set sweep interval time and is only measuring the spectrum when the gate signal is active. So when we have some time-related signals that we want to capture, this is appropriate way to do this. As the gate sampling mode measures the data only when the gate signal is active, we can make time-related measurements of pulse signals. But because the gate signal and the sampling time of the instruments may be not asynchronous, not all pulses of the light may be sampled when in a single sweep. To capture the full spectrum related to a given time point of time, we can use the max hold function and do repeated measurements of the spectrum to achieve the complete spectral shape of the signal. This operation mode can be time-consuming, especially with older models which just have the classical gate mode implemented. With our newer models, like our AQ6370E, we have improved the gate mode to achieve higher measurement speeds, especially for recirculating loop tests. But this can also be applied to burst signals. And now we will have a short look on the benefit of this mode. To measure this, I now change the trigger signal of the OSA to a trigger signal different from the periodic signal of the source. And if we then make some output and set the pulse condition, and then we will select, first we need to stop the sweep, then we can select the gate mode. In the gate mode, we have to set the gate sampling interval, which is determined with the required measurement sensitivity. We have to set the gate logic, and to adjust the measurement timing, we can set a delay to the instruments to capture the peaks properly. If we now do this measurement in the normal external trigger mode, we will see that it would take quite some time to measure the instrument, the signal, as the trigger signal for the gate mode are much slower than the signal of the pulse source. And you see, this would really take a long time. To improve this, we have implemented the gate mode, and in this device also with the advanced gate mode settings, so that the measurement in the max hold function is not needed. And we now just push the single sweep button, and we see the instrument is starting to measure in complete sweeps and capturing all the signal at the given time from the gate signal. And we just do it once again. You see, with every sweep, the signal is detected in different areas of the spectrum, which enables a much higher measurement speed for this kind of signal. When all the measurement is done, the instrument automatically sets to stop, and now you know you have captured your full spectrum according to the given timing that you have applied with the extra signal. And these were the pulse light measurements function that are implemented in all our OSA models, where the improved gate mode is only available for AQ6380, AQ6370E, 73E, and 74E. The live measurement we have already seen. And one more improvement regarding the pulse light measurement capabilities of our instrument was implemented in our new AQ6377E, our long wavelength spectrum analyzer covering a wide wavelength range from 1900 up to 5500 nanometer. As we learned before, in all the pulse light measurement modes, the top mode is not available. The great improvement of the new AQ6377E is that the instrument is now equipped with a high-performance chopper that is operating automatically according to the set sensitivity settings. And with this new high-performance chopper, now even the top mode functions can be combined with the pulse light measurement functions, which is then enabling a much higher measurement dynamic range than in normal operation modes without the top function. If you want to know more about the benefits of this instrument, we will showcase it at the Laser World of Photonics trade show in Munich end of June. So, and at this point, I can just point out to our next Yokogawa OSA seminar that will be held on the 21st of May in Ratingen in Germany. This is a free OSA seminar where we will explain fundamentals and capabilities of modern optical spectrum analyzers. And I want to invite you all to visit us at our booth at booth 431 at the Laser World of Photonics trade show in Munich from the 24th to the 27th of June 2025. And at this point, I can just say thank you for your attention and stay connected with Yokogawa not to miss out any further activities.